Topic 1H, order relations with whole numbers and decimals. So at this point, we're going to talk about basically putting things in order. In this case, let's start with putting some numbers in order from smallest to largest. And we'll deal with whole numbers to begin with. So what if I have 42,608, 76,492, 34,619, 21,456, 43,805, 51,200. So I've got 6 numbers that I want to put in numerical order, basically from smallest to largest. So if we're going to put numbers in order, then what we really want to do is we want to look at the highest place value and compare those first, and then work our way across to the lowest place value and put them in order like that. So without this, I see that I've got 42,000 something, 76,000 something, 34,000 something, 21,000 something, 43,000 something, and 51,000 something. So if I look at the largest place value, the largest place value for all these numbers is the 10,000s place. So basically, I could take these and group them by what 10,000s place we have. So I have, and I'm just going to start doing that in order. So in the 10,000s place, I have a 4, a 7, a 3, a 2, a 4, and a 5. So my smallest one is a 2, so I'm just going to go 21,456. And then I have a 3, 34,619. And then I see a 4, 43,805. I see another 4, 42,608. I see a 5, 51,200. And then I see a 7, 76,492. So these are in order by the 10,000s place, 2, 3, 4, 4, 5, 7. So far so good. Now I'm going to go into the next place over and make sure that those work. Well, these that already are in order by the 10,000s place, 2, 3, 5, and 7, those are good. My question is here. I've got 2 that start with 4, so I want to look at the next place. So these are the 2 that I want to focus on. I want to look at these because these are good. That's over 20,000, that's over 30,000, that's 40-something thousand, 40-something thousand, 50,000, 70-something thousand. So I know I'm good there, but these 2 I want to verify what order should they be in. So I go to the next place over. So now I'm going to the thousands place and I see 43,000, I see 42,000. 2 is smaller than 3, so I want to swap them. Just going to switch them one for the other and say 42,608 and then 43,805. So 42,608, 43,805. So now that I've got those in order, I can list them all in order as 21,456, 34,619, 42,608, 43,805, 51,200, 76,492. So I now have 21,456, 34,619, 42,608, 43,805, 51,200, 76,492. So I was able to put those numbers in order. We see that those are increasing: 21, 34, 42, 43, 51, 76. Now the most important thing with this is to make sure you're comparing the same place values. Let me show a very quick example of something where it may not match up the same. $6,412, 582,300, 12,461. So now I've got three numbers to put in numerical order. Remember, we want to go by place value, not just by the first digit. Notice that the first digit of each of these numbers is in a different place value. That's in the thousands place. That's in the hundred thousands place. That's in the 10,000s place. So in this case, we're going to go from smallest to largest. And if we look in the hundred thousands place, this is the only number that has something in the hundred thousands place. Essentially, 12,461 really has a 0 there. 6,412 has a 0 there. Remember, we talked about unnecessary zeros. So we don't write those, but that's really what's happening is there's a 0 in the hundred thousands place. There's a 0 in the 10,000s place. There's a 0 in the hundred thousands place. So when we compare, we go, oh, okay, well, hundred thousands, that's the only one that has anything in the hundred thousands place. So that's going to be larger than the other numbers. Then I get to the 10,000s place and I see, oh, wait, this one has a number in the 10,000s place. This one does not. It has a 0. So that's going to be larger. So then I get down to the thousands place. So basically with these three numbers here, I go, oh, well, if I'm putting them in order, then you have 0, 0, 5. Well, 5 is the largest of those, so I'm going to put that down here. 582,300. That's my largest number. Then I go to the 10,000s place. I have a 0. I haven't, well, it doesn't matter. I've already got that one written down. So I've got a 0 or I've got a 1. 1 is higher, so 12,461. And then the only thing left over is 6,412. So if we're dealing with numbers that don't have the same number of digits, then you can fill them in with zeros to get them to the same number of digits, and then it makes it pretty straightforward for putting them in order. Now, let's talk a little bit about real numbers. Real numbers can be broken into two parts. Real numbers can be broken into two parts. So if I have x, 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 I'm just putting placeholders here. Right? So if I have a bunch of x's here, so numbers, a decimal point, and then some more numbers, this part to the left of the decimal point or before the decimal point is considered the whole part. The whole part of the number. This number to the right of the decimal point or after the decimal point is known as the decimal part. So when we're dealing with real numbers, we can have a whole part, we can have a decimal part, and as you've seen, we can have numbers that have one or both of these, right? We could have 6.42. That's a real number with a whole part of 6 and a decimal part of 42. we have 97. A real number with a whole part of 97, it doesn't have the decimal point part. 0.76. I have a tendency, I like to put zeros before my decimal points, but there's nothing in the whole part is nothing, and the decimal part is this 7/6, the part to the right of the decimal point. So just a little relation of real numbers. So we can put real numbers, these numbers with whole parts and decimal parts, we can put those in order too. 6.172, 8.31, 4.19, 6.57, 9.44. So I've got 5 numbers that are real numbers. They have whole parts and decimal parts. If I want you to put these in order, our method really doesn't change from when we were dealing with whole numbers. When we dealt with whole numbers, we started at the largest place value and worked our way down, or the greatest place value and worked our way down. Here we have a ones place, tenths, hundreds, ones, tenths, hundreds, ones, tenths, hundreds, one, tenths, hundredths, ones, tenths, hundredths, and watch for that in the tenths and hundredths, right? So the greatest place value, or largest place value, is the ones place. So we're going to compare the ones places. And this time, instead of writing them down and then reorganize them, I'm going to actually work my way through and say, okay, so we've got 6, 8, 4, 6, 9. The smallest one was 4, so 4.19. Nothing in the 5. Then 6, we've got 6.72 or 6.57. So since the first digit is the same, we're going to look at the second digit, and we've got a 7 here or a 5 here. 5 is smaller, so 6.57, and then 6.72. Then we're going to look at the next one. We've got 8 and 9, so 8, 8.31. And then, last but not least, in fact, last and greatest, 9.44. So we can put decimal numbers in order the same way we can put whole numbers in order. So it works exactly the same. Most important thing when putting numbers in order is make sure that you're comparing the same place values. As long as you do that, you should be okay. Let's talk about repeating decimals. What is a repeating decimal? Repeating decimals are decimal numbers that once you get to the decimal side of it, the right side of the decimal point, at some point along the way, it starts having the same number over and over and over again, or the same numbers over and over and over again. 6.717171717171, right? Dot, dot, dot. Remember that dot, dot, dot? That's an ellipsis, and it means that it continues on forever like that. So we can see up front that it's 0.717171717171717171, and we would have to keep writing that down forever. So that's a repeating decimal. Now there are different ways that you can represent a repeating decimal. In this case, I wrote the repeating decimal over and over again a period of times, and then I put this ellipsis, the 3 dots, meaning that it continues that way forever. Now some people will tell you that to do that, you need to have it repeat 3 times before you put the ellipsis in place. So they would say the minimum you could do is 6.717171 ... And in my opinion, that's a pretty good idea to use, because anytime you are setting up a sequence or setting up a series of events and then want to say it continues on that way, you really should show 3 steps in that process, as opposed to only showing 1 or 2. So I agree that that's a very smart way to do it. So it would be good to follow that. And an example of why it's good to follow that is on your calculator, there's a button that's e to the x or e to the box. Well, that's the E stands for the Euler constant, and you don't need to worry about what the Euler constant is at this point, but let's just say it is an irrational number, which means it will keep going on forever and not ever get into a repeating state where you can say it just continues repeating. If I were to take E and raise it to a power of 1, we get that Euler constant, and you plug it into your calculator, and that's 2.71881828, and then it goes on to like 5, 9, so it goes on to other digits afterwards. Notice that we had 1828, 1828 repeated in here. You may look at this and go, oh, well, that's repeated twice, okay, we can keep going. But the next digit is not a 1. It does not go to 1828 again. So when you only have 2 times of something repeating, that's not enough to show that it continues repeating. So the 3 times is a very good idea. Another way that you can represent these repeating digits, because we can see that 7-1 repeats over and over and over again, is you can put a bar over the repeating digits. And that bar tells me that this 7-1 repeats over and over and over again. So 7-1, 7-1, 7-1, 7-1, 7-1, 7-1. So that's another way of representing repeating numbers, and you'll see that a lot, where you just put a bar. If you took 1 divided by 3 and plug that into your calculator will either give you 0.333333 and keep going like that forever, or as many digits as it'll show, or it may show 0.3 repeating. So there are multiple ways to represent repeating, and don't forget the G when you write repeating. Repeating decimals, you can either do it by having it repeat a few times and then put the ellipsis, or you can put the line over it. And you should look to see how does your calculator present something that's a repeating decimal, because it actually varies by the calculator how it's going to present it. A good example is, what if I take 3 divided by 11, and I plug that into my calculator? Depending on your calculator, you could get one of the following results: 0.2727272727, and then it just stops there because it runs out of decimal places that it can display. You could get 0.2727272773, and it stops there because it ran out of digits to display. And we might look at that and go 2727272773. Oh, okay, so it ended. It stopped, or what we call terminated. It terminates. It stopped. But that's not really the case. What happened is we ran out of decimal places. This number should have been a 2, right? If it's repeating, that would be a 2. and this number after it would be a 7? Well, if your calculator ran out of decimal places here, so it's got that last one, 2 followed by a 7, if you round to this decimal place, that 7 makes it round up to this 3. So recognize that that may happen to your calculator. It doesn't mean that it was 0.27273 and it ended. It means that your calculator rounded. Notice in this one that it stopped a decimal place earlier, so that would have been followed by a 2. Rounded gives you a 7. So that's a possibility. Or your calculator could represent it as 0.27 and actually give you the repeating bar over it. So that's a possibility. The final one that it could do, depending on your calculator, is some calculators, Casio's are notorious for this, will actually give this to you as 3/11. Because it will display it as the most simplified fraction that it can. So we get 3/11, and you have to tell it you want it in decimal form if you want it in decimal form. So you'd have to hit the SD button. To force it to put it into a decimal form. Otherwise, it's going to give it to you as a reduced fraction. So just be aware of that and how that can happen with your calculator. So it's good to check out your calculator and see what way does it represent repeating decimals. So this is a good one for that, 3 divided by 11. You can take any number divided by 9, any number divided by 11, and you'll get to see repeated decimals, and you can work with it. Now that we're familiar with repeated decimals, let's go to ordering some decimal numbers where there could be repeating numbers involved, right? So let's say 0.5556, 0.555555, 0.5 repeating, 0.5757. Okay, so we've got 4 decimal numbers and we want to put these into order from smallest to greatest. So what are we looking at here? Well, we have to recognize what they're doing. We're always comparing the first place value and working our way across, so we match up. We've got zeros in the ones place, so we're comparing the tenths place. So we can see that that comes out all the same with this. One of the most important things to keep in mind is if we have a repeating decimal like this, that it really has more of that number coming. Don't fall into the trap of saying, oh, well, there's a 5 there, this one goes on to another number, these go on, so this must be the smallest one. That's not the case. It's actually 0.5555555 repeating. So we get to the first one here, we have 5, 5, 5, 5, they're all the same. We get to the second digit and we have 5, 5, 5, 7. Okay, so we've got our largest one here, 0.5757. So I'm just going to check that off as we got that one, we used it. So coming out to the third place, we have 5, 5, 5. They're still the same. To the fourth place, 6, 5, 5. Okay, so 6 is larger than those 5s. So we have 0.5556. So that one's been used. And then we have here, we have 0.5. We go out to the next place. So that's we're going out to the fifth place. 1, 2, 3, 4, 5. We have a 5. Out to the fifth place, we have a 5. They're still the same. Sixth place, 5. This one still has another 5, right? It has 5s that are repeating. Seventh place, this doesn't have anything, whereas this one has another 5. So this 0.5 repeating is actually larger than this because at this point, this has a 0 there, even though it wasn't written in there originally. So we have 0.5 repeating. The 5 keeps going, which makes it larger than 0.5555555. So in order from smallest to largest, we have 0.55555, 0.5 repeating, 0.5556, 0.5757. So it gets fun working with these and paying attention to the different place values and is it repeating, should there be a number there or not, and how does it work with that. So it's good to play with that and look at some numbers and figure out how it works. So the last thing I want to deal with is relations, or order relations, which is just a way of comparing two numbers. So just a way of comparing two numbers, and there are three things that we use as part of that. We use this symbol, which means less than, this symbol, greater than, and this one you should be familiar with, equal to. Right? So our order relations. This number is less than that number, this number is greater than that number, this number is equal to that number. Now, people sometimes get confused with which symbol means what, less than, greater than, etc. What really matters is just looking at the symbol, the larger side of this symbol versus the smaller side, the larger side of the symbol versus the smaller side, right? It's bigger here and smaller here. Bigger here, smaller there. So your larger number goes on the big side, your smaller number goes on the small side. Your larger number goes on the big side, your smaller number goes on the small side. These are equal, so that says the two have the same value. So let's determine which of those order relations to put in place for some pairs of numbers. So let's just remember we could have less than, we could have greater than, or we could be equal to. So those are the three options that we're going to have. So what if I have the numbers 5 and 9, and I say, put one of these order relations in between this to make it a true statement? Well, we look at it and go, okay, 5 and 9, which one's bigger, which one's smaller? 5 is smaller than 9, 9 is bigger than 5, right? So obviously they're not equal. And we're going to put the smaller side next to the smaller number, the bigger side next to the bigger number. So therefore 5 is less than 9, smaller side pointing to the 5, bigger side going towards the 9. 4,578, 2,691. Use one of these order relations to make a true statement. Well, they're obviously not the same, so we got rid of equals. Which one's bigger, which one's smaller? 4,000 is bigger than 2,000, right? So this number is obviously the bigger number, so therefore the larger side is going to be on the side of 4,578. The smaller side is going to be on the side of 2,691. 4,578 is greater than 2,691. 3.7 and 3.7 repeating. Again, let's use one of these order relations to make a true statement. So we got 3.7 and 3.7 repeating. Are they equal? Is one bigger than the other? Well, what does this repeating bar mean? That means that this 7 is going to be repeated. So really, this is 0.7777, right? There's all these 7's continuing on. So now, which ones, they're not equal, right? This is 3.7 and it stops. This is 3.77777 continuing on. Maybe I should put that ellipsis in there just to imply that's what's going on, right? It's continuing, so if this stops at 3.7, this continues at 3.77777, this one is obviously larger, therefore 3.7 is less than 3.7 repeating. Let's try one more just to make sure we're good with this. What if I have 26.57 and 26.570? So I want to look at these. Is it less than, greater than, equal to? Which is the order relation I should use? Well, 2 and 20, those are the same. 6 and 6, those are the same. 5 and 5, those are the same. 7 and 7, those are the same. I've got a 0 here, I don't have a 0 here. But how much is 0? 0 is nothing, right? In fact, that's an unnecessary 0. If I get rid of that unnecessary 0, I have 26.57 and I have 26.57. Those two numbers are equal. Now, we may have a reason that we're representing something with this 0. Maybe this really is 0.570 and it was measured to that value, whereas this one was only measured to the 7. So there are reasons we may represent with that 0 or without that 0, but they are equal. So order relations with whole numbers and decimals.